Today, we're diving into a state of matter so unbelievably strange, it literally blurs the line between a particle and a wave. And you know what? It might just hold the key to programming reality itself.
Just think about it for a second. What if you could build, tear down, and move atoms around with the same precision as a laser beam? What if matter wasn't this fixed, solid thing, but was programmable? It sounds like something straight out of a movie, right? Well, the science is very, very real.
And the secret to all of this lies in a bizarre, super chilled state of matter. It's so extreme that it forces individual, totally separate atoms to basically forget who they are and merge into one single controllable quantum wave.
So how in the world does that even work? Well, to get it, you first have to understand that there are two fundamental types of particles in the universe. And honestly, this one little distinction explains pretty much everything, from why you can't just walk through a wall to how a laser beam actually works.
The difference between these particles is actually kind of fascinating. On one hand, you've got fermions. These are the particles of matter. Think of them as the introverts of the particle world. They refuse to be in the same quantum state. It's the whole reason my hand doesn't just phase right through this desk. But then you've got bosons, particles like light. They're the total extroverts. You can stack them all into the same state, which is exactly what's happening when you focus a beam of light into a single, super powerful laser point.
And that brings us to the Bose-Einstein condensate, or a BEC for short. This is what happens when you take those antisocial matter particles, the fermions, and you cool them down so much that you literally trick them into acting like those socialite particles, the bosons. They just stop being individuals and merge into this single, unified quantum wave. You've basically turned a clump of matter into a coherent beam, just like a laser.
Okay, so how do you actually convince a bunch of atoms to perform this quantum magic trick? Well, it turns out you have to create some of the most extreme, most insane conditions known to science.
I mean, we are talking about temperatures colder than the absolute deepest parts of outer space. You have to get ridiculously, fantastically close to absolute zero. That's the theoretical point where all atomic motion just stops.
The recipe to make one is as precise as it is extreme. First, scientists trap a cloud of atoms, something like rubidium gas. Then they blast it with lasers, but they're not trying to heat it up. They're strategically using the light to slow the atoms down, to literally knock the energy out of them, which makes them colder. For that final push, they use something called evaporative cooling. They basically kick out all the hottest atoms until what's left behind is just unimaginably cold. And that's when they finally merge.
And what you get at the end of all this is wild. The individual atoms, they kind of lose their addresses. Their quantum wave functions, which is just a fancy way of saying their probable location, they expand and overlap so much that they become one single thing. If you could see it, you wouldn't see separate atoms anymore, just a single, fuzzy, blurred ball of matter wave.
Now look, this whole idea of turning matter into waves, this wasn't just dreamed up last week. It has a super long and fascinating history that took it from being this wild what-if prediction to a Nobel Prize-winning reality.
It all kicked off way back in 1924. It was predicted by Nath Bose and, yeah, Albert Einstein himself. But it was so ridiculously hard to actually create that it just stayed pure theory for decades. Until 1995, when two physicists, Eric Cornell and Carl Wieman, finally pulled it off, and they deservedly got the Nobel Prize for it in 2001.
71 years. Just let that sink in for a moment. That's the gap between someone having the idea and someone actually making it happen in a lab. That really tells you just how monumental of a challenge this really was.
Okay, so we figured out how to make matter act like a wave. That is incredibly cool, no doubt. But so what? What's the point? What can this fit state of matter actually do for us?
Well, it turns out the applications are already shaping our world. BECs are absolutely crucial for developing things like quantum computers. They're used in ultra-precise sensors for MRIs and next-gen navigation systems, and even in detectors for gravitational waves. We've also created atom lasers with them and made real breakthroughs in lithography, the process used to make the microchips in your phone.
But there's always been this one massive roadblock. That incredible power has been locked away inside labs that can reach these insane near absolute zero temperatures. So it's been powerful, sure, but also incredibly impractical. But what if you could break free from that? What if you didn't need to be colder than deep space? What if you could unleash this power anywhere, anytime?
This is where the story gets really, really interesting.
Because in just the last decade or so, scientists have started to completely shatter those limitations, bringing these matter waves out of the extreme cold and into a much more practical reality.
Just check this out. In 2013, researchers create the first ever BEC at room temperature. That's a total game changer. And then, in 2022, they figured out how to create a continuous BEC, a matter wave that doesn't just flicker into existence for a moment, but one that can last indefinitely. These two breakthroughs basically take BECs from being a lab curiosity to a real, persistent, practical technology.
And this is where we go to the absolute bleeding edge of science, where the ideas behind the coldest matter in the universe are being connected to some of the hottest, most powerful forces we know. We're talking plasma and nuclear fusion.
And this is where a physicist named Gary Stevenson shows up with a truly mind-bending idea. What if you could use oscillating, or, sloshing, plasma to generate gravitational waves? Not just to detect them, but to actually create them on demand.
The basic concept is actually surprisingly easy to get your head around. Imagine you're in a bathtub. If you rock back and forth nice and evenly, you just make some waves. But Stevenson's theory says, what if you slosh that plasma asymmetrically? Like you push it hard and fast one way and then let it come back kind of slow. The idea is you could create a directional disturbance, not just in the plasma, but in the fabric of space-time itself.
So here's how the chain reaction would supposedly work. That asymmetrical slosh of plasma creates this specific kind of imbalance in its gravitational field, what physicists call it changing quadrupole moment. Now, according to Einstein's theories, that specific type of ripple is exactly what generates gravitational waves. So if you can control the direction of those waves, well, in theory, you can create thrust without shooting anything out the back. A whole new kind of propulsion.
And this is the grand finale, where these two completely opposite ends of physics might actually meet. The lessons we're learning from forcing atoms into a single coherent wave in a BEC, all those techniques for precise quantum control, are the same foundational ideas scientists think could one day be used to control the chaotic plasma inside a fusion reactor, to turn its incredible energy into a coherent, directional force. We're talking about connecting the coldest science with the hottest to imagine a whole new era of space travel.
So we've gone on this incredible journey, from the fundamental nature of particles all the way to a radical vision for pushing starships through space. It really makes you wonder, doesn't it? From controlling the quantum world one atom at a time to maybe, just maybe, surfing on waves of space-time. Could these matter waves be the ultimate key to unlocking our future?